Good morning class, and today we will start our discussion of laminar non-premixed flames. So the basic idea here is that in contrast with premixed flames where the fuel and air is mixed before the combustion process happens, in non-premixed flames the fuel and the air mixes in the flame front itself. So initially the fuel flow and the oxidizer regions are distinct, and at the flame front they mix and combine to form the burned gas products. Okay. They are also called laminar diffusion flames because the diffusion of fuel molecules and oxygen molecules to the flame front where they react and generate the flame region is the controlling process. So the diffusion process is the most important process in a laminar non-premixed flame, and hence they are called diffusion flames. So if you recall the example of a Bunsen burner, when the Bunsen burner at its base has certain holes for air, and it can run either in premixed mode or in diffusion mode. In premixed mode, the bottom holes here were open so that the air mixes with the fuel as it goes through the tube. In the case of diffusion flame, these holes are closed. So pure methane gas or pure LPG flows through the tube and comes out as a jet. And this jet then mixes with air at the flame front. So if you look here, what you have is a pure methane gas jet coming out of the exit tube, and when you ignite this jet, then a flame front is generated at the point where the jet is mixing with air. So inside the flame it's fuel, outside the flame zone it's air, and the fuel and air are mixing at the flame zone through diffusional processes. Hence it's called a diffusion flame. Diffusion flames are significantly more common than premixed flames because many of the liquid combustion or solid combustion processes where you are either burning charcoal, coal, or liquid kerosene, wax in a candle flame, there also what you are getting are non-premixed flames, because in those cases initially the fuel is in a different phase, either a liquid phase or a solid phase, and it's then vaporizing because of the presence of the heat originally from the ignition source or from the flame once the flame has been established, and these fuel vapors are mixing with air at the diffusion flame front and hence is generating the flame. So in those cases as well, what you are getting is a non-premixed or diffusion flame, because originally the fuel phase, the fuel vapors are distinct from the air which is outside. Today, in this set of classes, we will ignore the initial evaporation or phase change processes that are common in liquid or solid fuels, and we will look at purely gaseous diffusion flames like this Bunsen burner setup, okay, and see in what way it differs from the premixed flame kind of a process. Okay. So, physically, the premixed flame and the diffusion flame are quite distinct because you do not actually have a flame front that is propagating into your reactant mixtures, because there is no reactant mixture as such. The flame front is always stationary and the fuel and air are coming to the flame front from either side, okay, so through diffusion. So the flame does not have a velocity per se. So what we call the laminar flame speed that we discussed so extensively in the premixed flame, no such concept exists at all in diffusion flames, because the flame does not have a speed at all. Okay. Fuel is coming from one side, oxygen is coming from one side, and where they are mixing, the flame is being generated. Okay. So we will have to find different ways to characterize the flame. Okay. Another popular structure is what is called a co-flow burner. Okay, so let's look at the figure. So suppose we have two concentric tubes, an outer tube and an inner tube. Okay, through this inner tube, gaseous fuel is coming out, and through this outer tube, air is coming out. So air coming from the outer tube, fuel from the inner tube. Okay. In this case, the mixing is happening in this region separating the two gases, the fuel gas and air. Okay. So the mixing is occurring in this region and the flame is developing in this region. Okay. So in the boundary between the two flows, diffusion based mixing happens, and that's where the flame is being generated. These are called co-flow burner setups, and these are quite popular ways to create diffusion flames in within combustion chambers. Usually they are turbulent diffusion flames, but the basic structure is similar. You have a outer air flow and an inner fuel flow. Okay, and they are mixing at the edges, and these are called co-flow burners, as I discussed. The advantage of such a system is it does not require air on the outside to burn. So suppose within a closed combustion vessel, within an engine for example, or within a combustion chamber where there is no air as such, when it's burning continuously, the gas inside the combustion chamber will be a mixture of the product gases primarily. Okay, so there will be no oxygen. So the supply of oxygen has to be provided. So in that case, if we want a diffusion flame, this is one popular way to supply oxygen. Okay. Now here this YF is kind of the flame length. The RJ is the radius of the fuel jet. So basically the inner tube radius, that's the radius. So this is the fuel jet, and RS is the radius of the outer air tube. Okay, so RS is the concentric cylinder, outer cylinder, cylindrical tube diameter. Okay. In this case, two different structures are usually possible. What you have here is an example of an over-ventilated flame. So in this case, if the mass flow rate of air is greater than the mass flow rate that is required to completely oxidize the fuel, so you have m dot air on the outside and m dot fuel on the inside. So now the fuel is burning in a certain ratio. So the amount of air needed to completely burn the fuel, if the mass flow rate of air is greater than that, then the flame kind of closes out like this. And this is also true for a standard Bunsen burner case, because there is a lot of air on the outside environment. So in both cases, the amount of air that is present is greater than the amount required to completely burn the fuel. So such cases, a closed kind of an flame forms, like a closed flame, which is very common to see, because most of the burning that we have seen is where you are burning in an excess of air. Okay. So the same case here, if the flow rate of air is greater than that required to fully oxidize the fuel, then a closed kind of a leaf-like structure is formed. These are called over-ventilated flames. Okay. The other kind of flame that you get under some circumstances is, suppose you are burning and the fuel flow rate is greater than the air flow rate is less than what is required to fully oxidize your fuel flow. So the m dot f is such that the m dot f by m dot a ratio is on the rich side. So there is greater amount of fuel that is coming out compared to the amount of air that is required to fully oxidize the fuel. In this case, what is called an fan-shaped under-ventilated flame forms. So basically what happens is there is too much fuel, so the amount of air kind of decreases. So the flame kind of moves outwards in search of air. Okay. So then you get a kind of fan-shaped open flame. Okay. So a fan-shaped flame, which is called an under-ventilated flame. Okay. So then again you have a specific flame height, a specific and these RJ and RS is the same. So depending on the flow rates of air and fuel, the flame shape can be quite different depending on whether you are operating with an excess flow of air or an excess flow of fuel. So these examples that I showed you are essentially three-dimensional flames. So you have a complex, either a leaf-like 3D structure or a fan-like 3D structure going around this under axisymmetric conditions. It's also possible to develop one-dimensional diffusion flames as well. These usually do not have a significant practical application, but they are very useful for analysis, because one-dimensional flames, the structure is very simple. You can ignore much of the fluid mechanics that is happening. So you can look at what exactly is the chemical kinetics, heat transfer, and the other energy transfer processes that are happening without worrying about how the flame structure is and how you can properly model those things. So 1D diffusion flame is also possible, and a very common way to develop a one-dimensional diffusion flame is what is called the counterflow flame configuration. Okay, so let's look at the figure here. So here you have two opposed jets. Okay, suppose in an inert atmosphere you can think an air jet from the top and a fuel jet from the bottom. Okay, and in this case they are opposing jets, so the flow kind of collides with each other and a stagnation plane is formed. Okay, so the airflow streamlines go like this and the fuel flow streamlines go like this. Okay, and a stagnation plane is formed between the two jets. Okay, so now if you ignite the region here, a one-dimensional diffusion flame is formed just some distance away from the stagnation plane. So here usually the flame is formed in the air side compared to the fuel side. This is because usually the flow rate of air is much greater than the flow rate of fuel. Even if you look at a similar air-fuel ratio, the mass of air, even under the stoichiometric condition, the mass flow rate of air will be greater than the mass flow rate of fuel. Even if the amount of air is exactly that which matches the amount that is required to fully oxidize the fuel. So typically it is found that the flame is formed on the air side and the fuel kind of diffuses towards the flame across the stagnation plane, and the air is kind of here. Okay. So in such a kind of a stagnation region zone here, the details kind of we will discuss later if we have time, we will have this one-dimensional flat flame. A flat flame is produced. Okay. So this is very useful to find out the structure of the diffusion flame, the fuel concentrations across the flame, the fuel and the product concentrations. So this is very popular way to study diffusion flames in laboratory conditions. Okay. So now what determines where this flame surface is going to be? Okay. So if you remember in the last, in the premix flame conditions, the flame surface location was determined by the balance between the laminar flame speed and the unburned gas velocity. So it was inclined in cases where the laminar flame speed was lesser than the unburned gas velocity, so you get an inclined position. And it was also determined by where the flame is anchored near the burner edges, where the heat loss generated decrease and the boundary layer velocity kind of becomes equal to each other. So flame speed considerations and heat loss considerations kind of determined where the flame is going to be located. Now here flame speed does not exist, so how do you know where the flame surface is going to be? Now because it's a diffusion process, so in the flame front, the fuel molecules are diffusing into, air molecules are diffusing into from outside, and they are combining in the flame and then producing products, right? So the flame front acts as a sink of oxygen molecules and fuel molecules and a source of the product molecules, correct? And so the balance of diffusion is such that the flame front will be present exactly where your the rate at which fuel is entering the flame balances the rate at which oxygen is entering the flame in the stoichiometric proportion. Okay, So, so the flame will always be where the ratio of the fuel concentration and the oxygen concentration is at stoichiometric proportion within this region. Okay, because if the flame is at stoichiometric proportions, then the fuel is entering the flame and oxygen is entering the flame in perfect balance. All the fuel molecules are combining with oxygen, all the oxygen molecules are combining with fuel, and there is no excess fuel on the air side and no leftover oxygen on the fuel side. So where the balance is exactly perfect, the fuel comes out and becomes zero at the flame. The fuel concentration and oxygen concentration comes down and becomes zero along the flame. So the location, the flame is located precisely where the fuel mass fraction and the oxygen mass fraction is at stoichiometric proportion for that specific fuel molecule. So that is the condition that determines where the flame front is going to be. So in each of these various diffusion flame configurations, the flame surface is located where the fuel and the oxidizer mix in stoichiometric proportions. That is where the local equivalence ratio, and this is very important, the local equivalence ratio, because the fuel is on one side, oxygen is one side. So across the flame zone, the equivalence ratio is going to change very rapidly. Okay, so the local equivalence ratio is 1. Thus, the non-premix flame surface is the locus of all points where the local equivalence ratio phi, which is now a function of space x, y, z, is equal to 1. And it can also be a function of time if it's an unsteady flame. So if you have an unsteady diffusion flame, then wherever at a certain location the phi is 1, all the locus points, you will have a diffusion flame front established. So that's how you define where the diffusion flame front is being established. Okay. So now let's look at some quick examples of diffusion flames before we go to the next section. So yeah, so this is an example of a laminar diffusion flame I got from a paper, 2013 paper. So this is a co-flow burner, a very popular way. So air is coming out at 100 degrees centigrade and 20 centimeters per second. Fuel is coming out at 180 degrees centigrade, so it's a cycle heated fuel at 23.5 centimeters per second. And the reason it's heated is because the fuel that you are trying to burn is actually liquid fuel originally, so it's being pre-vaporized. So jet A, which is a jet fuel, SPK, another jet fuel, N-decane is also a kind of a compound that is present in a jet fuel or aviation fuel. So different types of compounds that are commonly found in jet fuels are being burned, vaporized here and flowing through this fuel tube. And this is the diffusion flame front. What they have shown here is kind of how you can do a CFD analysis primarily. So they have created a grid. So this is how the flame looks, and this is the radius. So the total fuel jet diameter is 10.9 millimeters, and the outer diameter is outer radius is 4.8 centimeters. Okay. And these are figures that show firstly the temperature. Let us look at the temperature. So 373 kelvins, dark green, 1940 kelvins, red. So the red region is where the most amount of heat is being generated. So you can see this flame front in the region of the extremely red region, and on the other side the temperature is decreasing quickly. So once again you get a kind of thin symmetric flame. There is excess air, so we have an over ventilated flame, so it's closed in on itself. And for different fuels it's slightly different, the flame location, as you would expect. And this is also a very common thing, is to find the amount of soot that is being generated. So diffusion flames usually produce in certain cases a significant amount of soot, which are unburned carbon molecules. This is because often while ideally the local equivalence ratio of the flame is quite equal to 1, and there is no leftover oxygen on the fuel side, usually some amount of oxygen bleed into the fuel side, so inside the jet, and then the fuel begins to burn at an extremely rich kind of a stoichiometric condition, away from the flame front. So if you look here, the flame front, for example, here is in this region, right? And the soot generation region is slightly below, so somewhere around the on the fuel edge of this flame front. Okay, so that's where the stoichiometry is going to be extremely rich. So and there the fuel will be burning in a very rich mode and producing a lot of soot. And the soot, once produced, can be imperfectly oxidized. So oxidation may be imperfect, so some soot will be left over. So that's why diffusion flames often produce a lot of soot, and you find this in candle flames. So all the yellow colored flames, the yellow color emission is emission from heated soot particles. So whenever a flame looks yellowish, it means it is generating a lot of soot. Okay, because it's the soot particles which are getting heated up and emitting that yellow color of your flame. So wood flames, charcoal flames, candle flames, you see all of them are quite yellow in the outer region, so they are generating a lot of soot. Okay, so that's the basic idea. Here I am showing you the two examples. This is the over ventilated case, and this is the under ventilated case for a co-flow burner, and this is your fuel side, air side. As you can see, the stagnation plane, and this is your flat flame, counter flow flat flame, flat diffusion. Okay, and this is an example from a researcher who had given a picture of it on his website. So this is kind of the air nozzle, and this is your fuel nozzle, and you see this beautiful plain diffusion flame being produced in the middle. Okay, so yeah, looking very nice. Okay, so before starting the complete analysis of the reacting flame, let's look at what happens when a non-reacting fuel jet enters a region of quiescent air. So suppose you have a fuel nozzle and it is emitting fuel. So it's the nozzle is entirely made of fuel, so methane suppose, or LPG or whatever is coming out into the air outside, and you have not yet ignited it. So then what is the velocity profile along the nozzle axis, jet axis? It's called a fuel jet axis. What is the concentration profile of the fuel and oxidizer in the transverse direction? So we can think of this as axisymmetric. So along it's symmetric, so circularly it's symmetric. So this is the x plane and this is the r plane. The theta plane, it's symmetric. So we can think of it as a 2D axisymmetric situation in cylindrical coordinates. Okay, and we are not yet igniting the fuel. So what is the kind of concentrations that are generated, velocity profiles that are generated before the ignition has taken place? So this is the case of a non-reacting constant density laminar jet. So we are also ignoring the fact that the fuel density and the air density will be different. So that difference in density often leads to buoyancy effects. So we are for now neglecting them. So to create a reasonably easy to understand analytical result and understand the physics, because that's the goal of the initial analytical results at least. Okay. So let's look at the jet and how it looks. Firstly, this is not the one. What is this? Yeah. So these figures are taken from your Turn's book, basically. So here is your fuel jet, the jet nozzle. The radius of the nozzle is R, capital R. So the diameter is 2R. This is where the nozzle ends. Okay, and it's ejecting gaseous fuel in a region of quiescent air. Okay. Now, as the fuel exits, it kind of expands. So the fuel jet region, the region where the effect of the fuel jet will be felt by the outside atmosphere, kind of expands along the downstream region. So this is kind of a boundary layer is produced. So outside of the boundary layer, the air is still quiescent. It has not felt any effect of the jet. Inside this layer, the jet has made its effect felt, and the width of this layer kind of expands outwards as you move further and further downstream. Okay, so physically what this means is, as the fuel comes out, its edges begin to mix with air, and this process is what is called an entrainment process. That is, air is being getting mixed on the outer edge of this jet of fuel that is coming out. Okay, so because of this entrainment process, the total mass that is being affected by the fuel jet is increasing as you move further and further downstream. So suppose in this location, the total amount of mass that is being affected by the fuel jet is lesser than a region further downstream. So the amount of mass of fuel and entrained air that is being influenced by this jet is increasing as you go further downstream. Obviously the fuel mass is constant, it's the air mass that is increasing with time as more of the mixing happens. Okay, and what happens very far downstream is eventually the fuel gets fully mixed with air. Okay, so what you are seeing here is basically what happens when you mix a fuel jet with air. Suppose so in a premixed case, this mixing happens downstream of your tube. Here the mixing is happening after you have ejected into the airstream, and so this is over time further and further downstream you will get a completely homogeneous mixture of fuel and air. Okay, but within this region there is more of the mixing process is still happening as you move further downstream. Okay. So if this happens, there is, just after the exit of a jet, a potential layer. So the fuel jet also within this small triangular zone has not felt the effect of air getting entrained. Okay, so the region here which kind of drops out very quickly is the region of the fuel which is kind of the free stream. Okay, so here the fuel has not felt the effect of air entrainment. So outside this region, the fuel is already getting mixed with the entrained air. Okay, so this is where the mixing is happening, and the mixing region is kind of expanding within the jet itself. Eventually this potential core kind of drops off, and here the mixing process entirely fully happens. So this is kind of these are the boundary layers on two sides, and they are expanding, and eventually the two boundary layers mix here, and so the mixing process happens to this entire region of your chip. Okay, so this is the potential core that kind of goes away as you go further downstream. So the distance of the potential core is along the axis is xc. Okay, and if you if you plot the velocity front, in this region the effect of the air entrainment is not being felt, and after that it is being felt. And for simplicity we can assume that the velocity profile as the fuel is exiting your tube is uniform. So you have a uniform velocity of profile at the nozzle exit. So if you take a cross section, transverse cross section along the R direction, and if you look at the velocity profile here, so this is Vx. Okay, Vx is the velocity at any certain x position. Okay, so x is increasing, x equal to 0, and it's going up. So Vx is the x component of velocity, and suppose you measure this x component of velocity exactly at the nozzle exit, then of course the velocity at the nozzle exit, we are saying it's uniform, it's equal to Ve, right? So here it's Vx by Ve is 1, so it's a uniform velocity up to R, and there is no velocity beyond that because the air at this point has not felt the jet at all, so it's 0. The Vx is 0. Okay. So now the mixing begins to happen. So if you go further downstream in this cross section 1, x equals to x1, so here you will see the Vx by Ve kind of has gone down from the value of 1, and this is because and this we will see the momentum is conserved. So the amount of momentum that is being imparted by the jet is conserved at any further location downstream, because all the momentum is coming from the fuel jet, and as the amount of mass of air being entrained increases but the momentum remains same, the velocity will have to decrease. Momentum is mass into velocity. So if the total mass is increasing, the velocity is decreasing. Correct? So what this means is the axial velocity at this point here is now less than VE, the velocity at the exit. So it goes down from 1, and this velocity kind of drops off as you move in the radial direction, because away from the axis more and more of the mixing has taken place, so the fuel jet has decelerated further and further. So you get this kind of a process, and you see this total radial distance up to which there is significant amount of velocity has now expanded, and this is example of this expanding effect of the jet. And if you go further, the same process happens. You have further decrease in velocity and further broadening. So it starts from an extremely steep square shaped profile, and then it begins to drop in altitude and broadens out. Okay, so that is what is happening as you move further and further downstream. Okay. And this graph here just plots the velocity, the x component of velocity along the central axis of the jet. Okay. So up to the potential core, the velocity remains 1, because up to this point the central region of the jet has not felt any effect of the air entrainment at all, because the mixing boundary layers have not yet converged to the central axis. So the velocity Vx0, that is Vx at r equal to 0, radial direction 1, we have up to this potential core xc point, this Vx0 by V is 1, and then it begins to drop off, and this value will be same as this value here. Okay, so this dropping is because the mixing effect is now into the axis, and this becomes greater and greater. So you have this kind of a slow drop off of the velocity profile. Okay. Now we can show that the fuel mass fraction also follows a very similar profile. So suppose this jet is pure fuel. So at the nozzle exit, the mass fraction of fuel is exactly 1. And this is what you can see. So this curve works for the fuel mass fraction as well. So at the nozzle exit, YF is equals to 1 up to capital R position, and then it drops off very quickly, right? Now, at this position here, because of the mixing effect, once again, mixing has affected up to the central region. So obviously the mass fraction of fuel has decreased from 1. So we again have the same profile, the similar profile. So you can actually normalize it and get the similar profile of YF, which is largest at the axis but still less than 1, and it drops off as the R continues to increase. And throughout this region, there is some non-zero mass fraction up to the edge of the boundary layer of the jet. Okay. And this broadening continues to happen. So as mixing happens, YF dilutes. So the amount of YF decreases at any point near the central region, but it broadens out. So there is more YF present in the outer edges as well, right? And you can also plot the YF0, so YF at R equal to 0 along the central axis, until the potential core ends. YF is 1, and then it kind of slowly decreases. So that's the basic kind of physical structure of how your jet looks like. Okay. So let's go back. So I have kind of explained this entire position here. The main interesting point that I also noted here, that the momentum is conserved along any x direction, because all the momentum was getting imparted by the jet. So the momentum, total momentum at the nozzle exit plane, x equal to 0, will be equal to the total momentum at any x plane further downstream. Okay. Now the total momentum at nozzle exit plane is rho e VE square pi into RJ square. So in my notes, instead of capital R, I have used RJ, the radius of the fuel jet. Okay. So instead capital R is replaced by R suffix J, just a different notation, nothing else. The exit velocity is VE. The exit density is rho e. So the initial cross section of the nozzle, circular cross section, is pi rj square, and you are multiplying it by the mass rho e into ve and the velocity ve. So that's why you get rho e ve square pi rj square. This is the momentum, total momentum coming out of your nozzle. And at any downstream direction, if you integrate over the entire r going from 0 to infinity, 2 pi r dr. So 2 pi r dr is kind of this perimeter into a differential thickness of dr. So 2 pi r is your circular perimeter. So you're integrating over the entire angle, theta going from 0 to 360 basically. So because of it's a symmetrical jet, so you have a kind of a circumferential symmetry along theta axis. So you get you have this 2 pi r dr is a differential volume across the entire theta direction, and you are multiplying it by rho into vx square. Vx square is the x component of velocity at that given location. Okay, Vx square is a function of both the radius and the x value. Okay, so if you remember, if you look at your jet at a certain location here, Vx will be varying along the radial direction, right? And it is also dependent on at what x position it is. So Vx is a function of both r and x. Vx square density is also a function of r and x in general, because as you are mixing fuel and air, if the fuel and air have different density, the density will also be varying. So this is your total momentum at any x plane further downstream. Okay, and these two must always balance. All right. The mass of fluid issuing out of the fuel jet is also conserved at any cross section at a distance x from the nozzle exit. So the mass of the fuel, so this is the fluid, is the fuel here, that is coming out of the fuel jet, is also conserved at any x plane. So if you multiply the mass fraction of fuel yf rx, also dependent on radius and x, you have the differential perimeter 2 pi r into dr, so differential perimeter element, into density into Vx. So this gives you the total mass flow rate from the fuel side. So you are this is the total mass, right? And then you have multiplied it by the mass fraction at that point of the fuel. So then you get the fuel mass flux basically. Okay, and this will be equal to the mass flux of fuel at the nozzle exit, because obviously in a non-reacting case, the amount of fuel is being conserved. So rho e ve pi r j square yfe. This is the total mass into the mass fraction of fuel at the nozzle exit, which is usually 1, but I have still given you the yfe in case it's not 1. So mass fraction of fuel at nozzle exit E. So these are two conditions that has to be satisfied. Certain simplifying assumptions. So I think I will stop here. So in the next class we will continue this derivation and see how we can analyze the entire case of a non-reacting jet analytically, and then we will look into the case of a reacting jet. So today I have just given you the basic physical picture, and tomorrow we will derive, in the next class we will derive the physical picture for an actual jet case. Okay. So thank you for listening, and we will meet after the in the next class. Okay, thank you.